Okay. So so in this part of the lecture, we will be discussing discretization of continuous time dynamical systems. So we had a very simple example in the previous example about the proportional derivative controller, when we approximated, like for example, dE by dt. Okay, we did the approximation as e of k minus 1 divided by t. So this is like a first order approximation, and this is only for the derivative, but we would like to have a more general way in which for example, if we have a transfer function in the S domain, we'd like to transform it into the Z domain right away. So is there a way to discretize a continuous time dynamical system from the Laplace domain into an equivalent or an approximate discrete time system representation in the Z domain? So that's what we're trying to ask. So we will explain like two of the most famous methods for doing this, and first is called a bilinear transform. It's a very famous transformation, the bilinear transform. Sometimes it's called the Tustin method. If you might meet this method, or it's also based on trapezoidal integration, and we will see why this is the case. So we know from the Laplace transform that 1 over s is an indication of the integration operation, right? So what we're trying to do is we try to approximate this integration. We try to approximate this integration by a trapezoidal integration. What does a trapezoidal integration mean? Okay, if you have a curve that looks like this, so you divide it into sections like this, and you approximate the integral by these trapezoids. Okay, so it's a kind of better than doing this the rectangular approximation. So because in the rectangular approximation you will have this relatively large error, so the trapezoidal integration is better error, so it's a kind of a good approximation for the integration in the discrete domain. So the transform is based on that the 1 over s will be equivalent to trapezoidal integration. So the actual bilinear transformation says that, okay, all you need to do is just, if you have the transfer function in the S domain, you just replace every S and you insert, instead of it, you put this 2 over t, okay, 1 minus Z inverse divided by 1 plus Z inverse. Okay, so this is the bilinear transform. So since we are looking after 1 over s, so let's see how 1 over s looks like. So that means that 1 over s will actually be the t over 2, right? 1 plus Z inverse divided by 1 minus Z inverse. So this is how the bilinear transformation is done. Okay, so if we say, okay, let's say that this Z domain transfer function is y divided by x, and what we want to prove now is that this discrete time transfer function, let's call it whatever, h of z, for example, we want to prove that h of z is actually doing this discrete integration, or this trapezoidal kind of integration. So how can we prove this? Okay, we can easily just multiply both sides. So when you do this, you'll get the following set of equations. So 2 multiplied by y of z minus Z inverse times y of z, right? This will be equal to t, this other term, multiplied by x of z plus Z inverse times x of z. Okay, and if you obtain the inverse Z transform, so you will obtain this difference equation. So it's y of k, you know that Z inverse y of k, y of z is actually y of k minus 1, right? And this is equal to t multiplied by x of k plus x of k minus 1. Okay, so far so good. And all we need now is just to rearrange the terms. So if you do very basic simple algebra, you will find that y of k will be equal to y of k minus 1 plus t over 2 multiplied by x of k plus x of k minus 1. So this is the difference equation which is describing our transfer function. Okay, so how can we show that this difference equation is indeed the trapezoidal integration? Well, you can do that quite simply. Okay, so this is an iterative version of the of this approximation. So for simplicity or for explanation, we will enlarge the sampling time t like this. So if this is y of k minus 1, this is the previous value of the integration. So we say that the new y of k is actually equal to the previous y of k minus 1, and you add to that, okay, so this is the value x of k minus 1, and this is the value x of k. Okay, and you can easily show that the area of this trapezoid is indeed this term. Okay, so this is the area of the trapezoid, and you add to it the previous area, so you are indeed performing a recursive trapezoidal integration. So this is a trapezoidal integration, and since we have proved that this is a trapezoidal integration, so that actually confirms the fact. If we go back again here, so that means that we have proved indeed that this transfer function is performing trapezoidal integration, so which justifies that we can set it to 1 over s, which is the continuous time integration. So okay, so this is the first method of transforming from continuous time to discrete time, and it's one of the very famous methods that is used actually. The second method is called the impulse invariance method. Okay, the impulse invariance. What does that actually mean? So the impulse invariance it's a very simple method. So all it says is that, okay, if you have an impulse response, okay, and you discretize this impulse response like this, so the impulse invariance says that we're gonna preserve the value of the impulse response at the discrete time steps when we transforming from the continuous to the discrete. So let's say, for example, we have g of s 1 over s plus 1. Okay, so we know in this case that g of t is going to be equal to e to the minus t, right? And g of k is e to the minus k times t, and therefore you can, so it's just by discretizing this function directly. So in this case, from the Laplace transform tables, g of z will be z over z minus e to the minus t. So so we have obtained the g of z from the g of s by just simply preserving the impulse response. So that's why it's called impulse invariance. So it means that we are not changing the impulse response. We are sampling the impulse response at the time intervals, and preserving that, and then obtaining the forward Z transform. So first we get inverse Laplace transform, then discretize, then we get a forward Z transform, and that summarizes the impulse invariance. Okay, the bilinear transformation is much more common because it's more general and easier to implement, but this is also one of the famous methods that are used.